Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks for coming. I think we should get started, even though we're only 5 minutes late. But we have a little bit of a different format today. We have 3 talks, and they're all joint projects by University of Washington interns and Microsoft Research mentors. So the interns are going to present, and it's pretty packed. I mean, we're going to try and stick to like 20 minutes for each talk with 5 minutes questions, which should still give us a little bit of time afterwards. But I mean, I know what these guys have been working on, and there's plenty more to talk about than just 20 minutes. So we'll see how we can stick with the time frame. For those of you who don't know the event, this is like the 19th in a series. So the next one is the big one, the 20th anniversary. And it's basically just a place to connect research from the UW with research from MSR and sort of make personal connections, meet people, and sort of socialize a little bit and keep the connection open between one side of the lake and the other. Normally we have 2 talks, one from each UW and MSR, but again, this time we're experimenting a little bit, and depending on how it goes, if anybody has suggestions about different kinds of formats that we could use, they'd be also very welcome. So for the 3 talks, there's actually only one of the mentors could barely make it. The other 2 are not here today. One is actually in Ottawa. Colin Cherry accepted a job at the National Research Council up there, so he's not in our group anymore. The 3 interns are Stanley Koch, Hoi Fang, and Alan Ritter back there. The 3 talks, so Stanley is going to start with hitting the right paraphrases in good time. It's joint work with Chris Brockett. Then the second one is a really nice title, Toward the Turing Test, Conversation Modeling Using Twitter. That's Alan's talk, and that's joint work with Colin Cherry. And then Hoi Fang is going to talk about joint inference for knowledge extraction from biomedical literature, and that was joint work with Lucy. So again, we'll try and stick to about 20 minutes and then 5 minutes questions.
I'll try my best. Hi, I'm Stanley Koch from the University of Washington. My talk is on hitting the right paraphrases in good time. So this is the overview of my presentation. I'll begin with some motivation, then I'll cover some background, then I'll go into detail about our system, hitting time paraphraser. Then I'll describe some experiments, and finally I'll end with some future work. So the goal in this project is to build a paraphrase system, a system that takes as input a query phrase, such as is on good terms with, and outputs a list of paraphrases, such as is friendly with, is a friend of. Several applications can benefit from a paraphrase system, such as query expansion, document summarization, natural language generation, and so on. So in the application of query expansion, a search engine could receive a query phrase from a user. Then the search engine could provide the query phrase to our paraphrase system and obtain a list of paraphrases, which is then returned to the search engine. The search engine could then retrieve documents that are relevant not only to the original phrase, but also relevant to the paraphrases, thereby improving the quality of its results. I'd like to point out that our system, as well as the systems that we compare against, uses an additional resource in the form of a bilingual parallel corpora. So what's a bilingual parallel corpus? In such a corpus, we have sentences from 2 languages. Over here, sentences English and German. So these sentences are aligned, and the phrases in the sentences are also aligned. For example, under control is aligned with unter control. I'm not too sure whether I'm pronouncing the German right, so please bear with me. And over here, in check is also aligned with unter control. Now, from all these sentences, from these phrases, we can count the number of times that a phrase occurs, as well as the number of times that an English phrase co-occur is aligned with a German phrase. This allows us to obtain phrase tables. So, for example, if under control appears 4 times in this corpus and 3 out of the 4 times under control is aligned with Untitled control, then the probability of the German phrase given the English phrase would be 3/4 or 0.75. Now, these phrase tables are used by our system as well as the systems that we compare against. So in 2005, Bennett and Callison and Birch introduced the BCB system. I named the system after the authors. So this is a paraphrase system, and it works as follows. It computes the probability that E2 is a paraphrase of E1 by summing over all foreign phrases, German say, of the product of E2 given G and the probability of G given E1. Straightforward approach. And if you have multiple corpora, simply sum over all the corpora. So in 2008, Callison and Birch improved upon this system by cleverly introducing syntax. So if you look at the two equations used by the systems, you can see that they're very similar. What SBP does is that it introduces syntax over here. It constrains the paraphrases E2 to have the same syntax as the original phrase E1. And this syntactic information is obtained via parse trees. The interesting thing to note is that not only does it use the leaves of the parse trees, but it also uses the subtrees inside the parse tree. Now, this is a very general, high-level description of SBP. For details, I'll refer you to the paper. Now, we can take a graphical view of these two approaches by considering the phrases as nodes. So over here, I got all the English phrases, German phrases, French phrases, let's say. And an edge exists between two nodes if there's a corresponding entry in the phrase table. Now, once you take the graphical view, we can see that the SBP approach, what the SBP approach is actually doing is to sum up the probabilities along paths of length 2. So it's summing up the probabilities along this path and this path to get the probability of E2 being a paraphrase of E1. Now, once we see things graphically, we can think of several ways that we can improve upon this system. First, there's no reason why we should restrict ourselves to paths of length 2. If we consider paths of length 4, then E3 over here could very well be a good paraphrase of E1. By tracing this path of length 4, and E3 could be a good paraphrase of E1 if the probabilities along this path are fairly high. Second, note that this graph is a bipartite graph, with English nodes on one side, foreign languages nodes on the other. There's no reason for us to restrict ourselves to bipartite graph. We can have general graphs. Lastly, we need not restrict nodes to represent phrases. This is a graph. Nodes could represent anything. Specifically, we could have nodes to represent domain knowledge. So our system leverages these 3 points to improve upon the state of the art. And it does so using the notion of random walks and hitting time. So let me quickly cover the background on random walks and hitting time. Now, the term random walk is self-explanatory. It's just a walk by traversing edges randomly in a graph. I'm just going to illustrate this using this simple graph over here. Say we start at node 1. Next, we randomly pick a neighbor of node 1 according to the transition probability. So there's a probability of moving from node 1 to 2, probability from 1 to 3, and 1 to 4. And all these probabilities sum to 1. So using these probabilities, we randomly pick 1. Say we pick 2, then we move to 2, and we repeat the process. So next step, we could have moved to node 3. So a simple idea of random walks.
You said you moved to a neighbor node. How did you get from 3 to 4?
So 3 to 4 is 3 and 4. They are not neighbor nodes because there are no edges between them. So they are first to move to 3 to 1 and then 1 to 4. Yeah, okay. So what's the hitting time? The hitting time from node I to j is the expected number of steps starting from node I before node j is reached or hit for the first time. The intuition here is that the smaller the hitting time, the closer node j is to I. That is, the more similar node j is to I. In 2007, Saka and Moore introduced the notion of truncated hitting time, where random walks are limited to a fixed number of steps, let's say t steps. In 2008, they improved upon their results by showing that you can compute the hitting time efficiently and with high probability by sampling random walks. So each sample is a random walk. Now let me show you one such sample. Again, we start at node 1. The box over here will show you the order in which we traverse the nodes, and I limit the random walk to have t steps, to have 5 steps. So let's say that next we move on to node 4, then to 5, then to 4, to 6, and finally to 5. So 5 steps. And these are the hitting times. The hitting time from node 1 to 1 is 0 because it started at node 1. From 1 to 4 is 1 because it just took 1 step to go from 1 to 4. 1 to 6 has 4 steps because it took 1, 2, 3, 4. 4 steps to reach 6. And hitting time for node 2 and 3 are set to the maximum of 5 because they are not reached at all. So this is how Saka and Moore define truncated hitting time. Now, how do we compute the hitting time from all these samples? As is the usual case, we define a random variable xij. And xij is the first time node j is hit starting from node i. And if the random walk never hits the node j, then xij takes on the value of t. Then hitting time hij is just the expected value of this random variable, and we compute this expected value by taking the sample mean, the straightforward approach. Now, Saka and Moore showed that with high probability, our sample mean deviates from the true hitting time by a very small value if we are able to sample at least this number of samples. So n is the number of nodes in the graph. So that's the background. Let's move on to our system, the hitting time paraphraser. Just a quick recap. Our system HTP takes as input a query phrase. Phrase tables could be more than one. These phrase tables could be English, alignments of English to foreign languages, as well as foreign language to another foreign languages. And it outputs a list of paraphrases. And it ranks the paraphrases in increasing order of hitting times. As mentioned earlier, we could create a graph from these phrase tables with nodes representing phrases and ages existing between nodes if there's a corresponding entry in the phrase table. Now, this is fine if we have small phrase tables. However, for our data sets is fairly huge, and we're going to do this, we're going to end up with a very, very big graph, which is not trackable. So what we do is, to start from the query node and then perform breadth first search up to a depth of d or to a maximum of some number of nodes. In our experiments, we use a depth of 6 and maximums of 50,000 nodes. Now I'd like to zoom into the nodes at the periphery of this graph. Some of you might be asking the question of, so how do we handle the transition probabilities of edges that goes outside of this graph, especially those edges that crosses the periphery? We use a straightforward approach, introducing a placeholder node, collapse the edges together, and sums up the probability. And this placeholder node have a transition probability of 0.5 to the blue node and a self-transition probability of 0.5. Now, this is a heuristic approach that works pretty well as you'll see in our experiments. So now we are at the steps where we have created the graph from breadth first search. Now we could proceed to draw the samples, the random walks. We run m truncated random walks to estimate the truncated hitting time of every node in the graph. We limit the random walks to have 10 steps, and we draw 1 million samples. So with these numbers, the numbers of t and m, we could be 95% sure that our estimate of hitting times is no more than 0.03 away from the true hitting times, which is pretty good estimate. Once we have this random walk, once you perform this, once you've drawn all these samples and estimated the hitting times, we could rank these nodes. And we could find those nodes with hitting times of t. Now, intuitively, these nodes are nodes which are pretty far away from the query nodes, and therefore they're not very similar to the query nodes, and we could just throw them away. This helps to prune the size of the nodes even further. Now, once we have this prune graph, we can proceed to add more nodes to this graph to supplement the knowledge. We do so by adding what I call feature nodes. There are 3 kinds of feature nodes. The first is n-gram nodes. So over here, I show a snippet of the prune graph. Again, the brown nodes are the English phrase nodes, and you have the foreign languages nodes over here, blue and purple. To avoid clutter, I'm just going to remove the foreign languages nodes, but just bear in mind that they're still there. So n-gram nodes are pretty clear idea. So we have all these n-gram. We use 1 to 4 grams. There's an H between reach and reach the objective because this phrase contains this unigram. And there's an H between achieve the and achieve the aim because achieve the aim contains this bigram. Why do we introduce this n-gram node so as to capture the intuition that if two phrases have lots of unigrams, have lots of n-grams in common, then it tends to be closer together. That is, they tend to be more similar. The next kind of nodes are syntax nodes. I put syntax in quotes because it doesn't really correspond to syntax as what you obtain in the parse tree. What we do is we classify certain words, things like articles, things like interrogatives together into classes. And we mark whether each phrase begins with that class. For example, over here, the objective is linked to start with an article because it starts with the word the, which is an article. And likewise, for the aim has this link as well because there is an article. Whose goal is and what goal is are linked to the nodes start with interrogatives because whose and what belong to a class of interrogatives. So again, these nodes capture the idea that if you start and end with the same class of words, then you tend to be pretty similar, like good candidates for paraphrases. Lastly, we have this not substring of nodes. Why do we have this? We noticed in our experimental results that lots of paraphrases, lots of bad paraphrases were actually paraphrases which are substrings or superstrings of one another. We found that things like reach the was frequently returned as a paraphrase or reach the objective just because it's a substring of the paraphrase. Now clearly this is a bad paraphrase. So what we do is we include a node over here called not substring or not superstring of. This node will have a link to the query phrase, assuming that this is a query phrase, and all the other phrases will be linked to this node if it is not a substring or superstring of the query phrase. So this helps. So such nodes will be closer to the query phrase. So now there are 4 kinds of ages emanating from an English language phrase. I forgot to mention that we could also have features, similar features for the foreign language nodes. But in our experiments, we did not do so. We could easily add those nodes as well. But anyways, for each English phrase nodes, there are 4 kinds of ages. Ages that goes to the regular foreign language phrase nodes and to the 3 types of feature nodes. Now the question is, how do we divide the probabilities, the transition probabilities of emanating from these English nodes? Because P1, P2, P3, and P4 have to sum to 1. So we did so by tuning on a small held-out set of data. We just found that P1 equals to 0.1, P2 equals to 0.1, P4 and P3 equals to 0.4 tends to work pretty well. Some of you might be wondering why is P1 set to so low. Now note that this information has already been used when we first construct a graph and prune it down. So we found that we need not give it too much weight anymore because it has been used to pre-prune the graph to a good set of candidates. So now we're at this stage where we've added the feature nodes. Once you've added the feature nodes, we can proceed again to draw M truncated random walks, estimate the hitting times of all the nodes, rank the nodes in increasing order of hitting times, and return them. Then the return nodes will be the paraphrases of the query phrase. Now, how well does our system perform? Here comes the experiments. We use the Europal dataset. This Europal dataset is a dataset of minutes of European Union proceedings. These minutes are written in 11 languages, translations of one another. We use 6 of these languages: English, Danish, German, Spanish, Finnish, and Dutch. There are about 1 million sentences per language. And the English sentences are aligned with the foreign languages ones. The English foreign phrase alignments are done by Giza++, and this is done by Callison and Birch. We use their data, which is available from the web, but they do not have the foreign phrase alignments. So these are done using the MSR NLP aligner by Chris Quirk. So the systems that we compare against are the SBP system. Again, this system is available on the web. It's a Java implementation. And we also did a lesion study investigating how HTTP does without the feature nodes and how HTTP does if it just works on the bipartite graph rather than general graph. We also used the NIST dataset. In the NIST dataset was originally used for machine translations. Well, it has 4 English sentences per Chinese sentence, and they're altogether about 33,000 English translations. What we did was to randomly sample 100 English phrases from the 1 to 4 grams in both the NIST and Europar datasets. So these 4 grams appear in both of these datasets. We exclude things like stop words, numbers, and phrases containing periods and commas. Now, for each of these randomly sampled phrase, we randomly select a sentence from the NIST dataset that contains that phrase. Then we substituted the top 1 to top 10 paraphrase for that phrase. So this means that we evaluate the correctness of the paraphrase in the context of the sentence. Now, we did manual evaluation. We gave it 3 scores. We gave each paraphrase 3 scores. So a score of 0 means that the paraphrase is clearly wrong, it's grammatically incorrect, or it does not preserve meaning. A score of 2 means it's totally correct, grammatically correct, and meaning is preserved. A score of 1 means somewhere in between, where there are minor grammatical errors, things like subject-verb disagreement, the wrong tense, etc. The meaning is largely preserved, but not completely. So we deem the paraphrase to be correct if it's given a score of 1 and 2, and wrong if it's given a score of 0. There are 2 evaluators, and the inter-annotator agreement, as reflected by kappa, is 0.62. Now, this corresponds to substantial agreement between the 2 evaluators. So, let's look at the comparison between HTP and SBP in detail. First, I'd like to point out that SBP only returned paraphrases for 49 of the query phrases. So let's focus on these 49. Let's focus on the top 1, the top paraphrases written by this system. HTP got 0.71 of these top 1 paraphrases correct, and SBP 0.53. So let's suppose that we consider the top K, where K is the number of paraphrases written by SBP. For example, SBP only returned 3 paraphrases, so over here we look at the top 3 for HTP. And the performance is 0.56 versus 0.39, so HTP is still doing better. So how does HTP perform if you look at the top 10 paraphrases for HTP system? We got a score of 0.54. So let's change our focus on the 51 paraphrases that SBP give us no results. How do we perform? How does HTP perform? For the top 1 paraphrase, we got a score of 0.50, lower than what we got for the 49 top ones. And overall, for the top 1, we got a score of 0.61. The corresponding number for SBP is 0.53. Now let's look at the top 10 paraphrases for this bottom 51 queries. We got a score of 0.32. And overall, the system got, looking at top 10 paraphrases, for all queries, we got a score of 0.43. The number of correct paraphrases is 420. For SBP, the corresponding score is 0.39 and 145. So there are lots of numbers going around here. So what you should note is not only are we returning more correct paraphrases, 420 versus 145, we are doing so with higher precision, 0.43 and 0.39. Okay, I should hurry up. Okay, so how does HTTP compare to HTTP no features? That means suppose you don't use the feature nodes. This is a simple comparison because both systems retain the same number of paraphrases. If you look at the top 1 paraphrase, using features does better. We look at the top 10 paraphrases, again, using paraphrases does better. So it's pretty clear that using features, we do better. Now how about HTTP versus HTTP on a general graph versus HTTP on a just restricted to the bipartite graph? So the bipartite graph does not return paraphrases for 5 of the queries. So let's look at the 95 queries for which HTTP did return paraphrases. Looking at top 1, HTTP got 0.62 and HTTP bipartite 0.58. Looking at the top K, where K is the number of paraphrases returned by the bipartite, HTTP bipartite, we did better as well too, 0.46 versus 0.41. Now let's zoom into the 5 queries for which HTTP bipartite returned no phrases. Now these are the harder ones, so we got, for top 1, we got accuracy of 0.4, and overall, for top 1, you got 0.61, and the corresponding number is 0.58 for HTTP bipartite. If we look at the top K, this figure is 0.2. And overall, over the top 10 paraphrases, our system got 0.43. As before, 420 correct paraphrases. Corresponding number for bipartite is 0.41 and 361 correct. Again, not only do we get more correct paraphrases, we do so at higher precision. How about the timings? So HTP took about 48 seconds per phrase. And the HTP no features, the bipartite was around the same ballpark. It's faster because it doesn't use as many features. But SVP took about 468 seconds per phrase. Now note that when you look at these times, it's good to remember that the HTTP systems are implemented in C# and SVP in Java, and they're really using different kind of data structures. So just bear this in mind. So future work. For future work, we'd like to apply HTTP to foreign language paraphrases rather than just English ones. We'd like to evaluate HTTP's impact on applications. For example, we want to see whether we could improve the performance of resource-sparse machine translation systems by putting paraphrases into the phrase tables used by such systems. We'd like to add more features, even features used by SVP. We'd like to add like full syntactic trees to see whether they'll boost the performance of our system. So in conclusion, I presented to you a paraphrase system based on random walks. It uses the intuition that good paraphrases have smaller hitting times. It's able to handle a general graph, could make use of paths of length larger than 2, and it makes it easy to incorporate domain knowledge. And from our experiments, we see that HTTP outperforms the state of the art.
So, if I understood right, you do the random walk, then you prune the nodes, then you add in the features, and then you do another random walk.
Right.
So why didn't you add the features right at the beginning?
Because it'd be too large.
Okay, so it's just an efficiency thing.
Yeah. Right. Couldn't hold it in memory.
Do you think your proposal will work for Indo-European languages?
As Indo-European languages?
Europe, I mean, these are Indo-European languages.
So these are Indo-European languages? I'm not too sure. But
Mostly.
yeah. Okay. Chris says obviously. So
I think there was, Finnish was in there somewhere.
Finnish was in there.
Finnish was in there. Okay, so.
So to follow up on that, I'm curious how much the morphological simplicity of English. So when you try this in other languages, I'll encourage you to try something like Finnish early on, because it's got much more morphological complexity, and that might give you some data sparsity problems that you're not seeing in English. So just see how that plays out.
No, quite. And the reason I put it, the reason I have such like put in Finnish there, and if you look at the languages, I chose it such that there's a good spread of languages, whether the languages are really similar. So I think Finnish was quite different from.
It is. English and German and Dutch are all very similar, so it was good to have Finnish. But when you said you wanted to do trying this on foreign languages instead of just English, I thought Finnish would be a good place to start.
Okay.
And German too, but Finnish especially is going to give you the morphological complexity.
Thanks. So your results were based on whether or not your paraphrases were scored 1 or 2. So it's either they are correct or they were acceptable. Do you
correct or totally wrong? 1 or 2. Yeah, that's right. 0 or 1.
So, but you counted as a positive paraphrase if it was either totally correct or if it was, there's some morphological issues, but it was mostly okay. Do you roughly remember what the numbers were if you just looked at the ones that were completely correct?
I'm afraid not, but I definitely could pull that out simply enough. Yeah.
The criteria for really close were things like if we inserted, we didn't do any modification. So if it was an interesting time and the substitution was wonderful time for interesting time, then we still had "and" floating around. So the sort of thing that could be corrected fairly easily, and the word grammar checker was considered.
Right. Well,
close. So in order to say we're getting very close, we might have to do some manipulation here.
Right. Well, specifically because of that, because if you then want to include this into a phrase table, so if you're getting positions of 0.6 or something, that still means that 2/3 of what you'd be putting in your phrase table is wrong, or sorry, 1/3 of what you're putting in is noisy, right? So you'd only want to put in you want to add into your phrase table paraphrases that are actually correct, right, or as correct as possible. You want to try and minimize how much work you have to do on it.
Right. The issue is when you have the phrase table, where are you applying it? The particular instance that we had at that particular point might be had an interesting time with Anne. We can't predict that we're going to have, we might have something like, instead of had Anne, we might have something like, probably a good substitution there. Thank you for the, thank you. Well, thank you for the suggestion, yes. So thank you for the interesting time is, or the wonderful time. You might have those being, I mean, they're not really necessarily good paraphrases, but just, let's say they are for a moment. We don't know where the substitutions are actually going to be. So it's perfectly legitimate to put them into the phrase tables. In the particular environment where we tested them, they may be
So if I may,
close but just a little off.
So one way to address that issue of having that wanted noise, bad values would be, we could use the hitting times metric. And we could just say that, well, if your hitting time is smaller than this, then we keep it, otherwise you throw it away, otherwise you're bad. So that would allow us to get some threshold with which you could prune out all the so-called bad paraphrases.
The fact that you're still able to get 2/3 of what you decide is paraphrases, the 2/3 of them are good using this fairly straightforward method.
So these 2/3 are, I do not have a threshold there, so I've just returned, let's say, top one. Just look at the top one. Yeah.
On the thresholding, so how do you decide on the stopping condition, or what's the threshold of?
You're going to have, if you're going to use the threshold and the hitting time to choose, then really we have some kind of a. Okay, one is obviously to have some manual evaluation to look at. It is a good threshold evaluate. The second would be a better one where we have an application to tell us. Then we could tweak it.
Your experiments.
Over here, I didn't use a threshold. Just say that return. Just look at the top one score and the top up to the top 10 score.
Okay, but some of your graphs you have more than 10 characters.
That's right. There are more than 10, but only consider up to the top 10. Yep. Well, thank you very much.
Okay, so from large graphs, we're going to really small texts now, to the world of, 140 characters or less?
Right.
But many of them. And we're going to be introduced to the Turing test, which is something really new. So Alan is going to take it.
Okay, thanks, Michael. Okay, so I'm going to talk about modeling conversations on Twitter, and this is joint work that I did this summer with Colin Sherry and Bill Dolan. Okay, so first some motivation. So why would we want to model the way that people have conversations? So I think that the sort of main motivation for this is if we want to build conversational agents that are able to go sort of beyond just scripted dialogues and kind of say things sort of more impromptu and have more of a conversation with the user. And also if we want to build chatbots that are able to do more than just sort of parrot back what you said to them in a slightly differently phrased way. And some other possible applications for this include sort of like social network analysis, better web search for conversational text, things like forums and blogs and whatnot, and question-answer pair extraction. Okay, so what does Twitter have to do with modeling conversation? So most of the conversations on Twitter look something like this. It's just someone broadcasting information about their life to all their followers, and probably nobody cares. But and this is sort of not conversational, but somewhere between 10 to 20% of the posts on Twitter are actually in reply to another post. And these form sort of short conversations. So I've just shown a short example here. So this user said, I'm going to the beach this weekend. I'll be there until Tuesday. Life is good. Someone else responded to them saying, enjoy the beach. Hope you have great weather. And then they responded by saying, thank you. And that ends the conversation. And this is sort of a very typical kind of conversation that we'd find on Twitter. So we gathered a whole bunch of conversations from Twitter using their public API. And so we did this basically by watching the public timeline, which gives us 20 randomly selected Twitter posts per minute, And we use that just to get a random seed of Twitter users. And so from there, we can kind of crawl all the users that they're following and crawl their followers and so on, and then basically query to get all the posts of each of the users that we have. And so if any of those posts are in reply to another post, then we can kind of follow that back to collect the conversation. And so we got a lot of conversations. We got about 1 million conversations of length 2, 200,000 of length 3, 100,000 of length 4, and so on. And you can see that the frequency seems to drop off very quickly with the length of conversation. And in fact, if you plot frequency versus length on a log-log scale, it looks pretty much linear, and this sort of indicates that it's likely to be a power law, which I think is kind of interesting. So our basic hypothesis is that there's some kind of latent structure behind how people have conversations. So basically, each post can be classified into a class which describes its purpose in the conversation. So you might see like an initial status post followed by a comment and then sort of followed by a thank you. And this is sort of the kind of thing we want to model. And so further, we're saying that there's sort of a Markov property and that each type of post depends only on the previous one and not on anything else. And then the words in each sentence depend on the type of post, or the dialogue act, I guess is I'm going to call it. So in an initial status post, the word I is going to have high probability, and then we're going to see a lot of verbs like going, because the person's sort of describing what they're doing. Whereas in a comment, you might see you with very high probability as opposed to I, and then words like enjoy and hope and so on. But then there's also these other words that sort of don't have anything to do with the dialogue act, but are just sort of about the topic of the conversation. And so in this example, we see words like beach, weekend, Tuesday, weather, and so on. And so these don't indicate the dialogue act, but they're just kind of sprinkled throughout. And they're all sort of semantically related to each other. Okay, so in order to model these dialogue acts and the transitions, we looked at these content models from the summarization literature. And they were used specifically for multi-document summarization on news articles. So basically, they were looking at very specific genres of news articles. For example, articles all about earthquakes. And they found that typically people will sort of, in the first sentence, describe the location and the magnitude of the quake. And then maybe in the second sentence, they'll tend to describe how many people were killed or something like this. So they have sort of a very predictable structure. And they modeled that using hidden Markov models, basically in which the states emit whole sentences, and so they have a language model for each state that's sort of the emission model for the HMM. And then they learn the parameters using Viterbi EM. Okay, and so here I've just shown sort of a graphical model representation of what they did. And so this is basically just a Bayesian network where each dialogue act depends on the previous one, and then it emits a bunch of words. And so these boxes are this sort of plate notation which represents replication. So each act is generating a bunch of words independently. So you can read this box as like a sentence, basically. Okay, so this looks like really nice for what we want to do in terms of modeling dialogue acts in Twitter conversations, because it models this transition between latent structure, which corresponds, I think, very well to the idea of what dialogue acts are. And in addition, it's totally unsupervised. And so we don't need any training data or labeled data in order to be able to do this, which is really attractive. So there's a couple problems with this, however. And so if you just apply this naively without doing any kind of abstraction, it tends to group together sentences that belong to the same topic instead of the same dialogue act. And so in order to deal with this problem, Barsley and Lee masked out all the named entities in the text. But this is a bit more of a problem for us because we can't rely on capitalization to do a good job of identifying named entities in Twitter. And so if you don't sort of deal with this, you'll get things like all the sentences involving Seattle will sort of get clustered into the same sentence. Or it's the same cluster, excuse me. So what we really want are clusters like status, comment, question, response, thank you, and not clusters about like iPod, sandwiches, and vacation. And so we ran the content modeling approach on our Twitter data, and we found this is just sort of one example of one of the clusters we got. And you can see here these sentences don't really have anything to do with each other in terms of dialogue act, but they're really very much on the same topic. They're all sort of about web browsers and operating systems. So you see words like Safari, Windows, iPhone, Chrome, Firefox, and this kind of thing. So this seems sort of problematic for what we want to do. So our goal basically became to separate out the vocabulary into words which indicate the dialogue act, and then conversation-specific topic words. And in order to do this, we used an LDA-style topic model where basically each word is going to be generated from one of 3 different sources. So it could be just general English, and this is just sort of a way to flexibly model stop words. It could be specific to the conversations vocabulary, so these are like topics, or it could come from the dialogue act. And hopefully, we'll get sort of a stronger signal here. And this is similar to the model that Lucy and Arya Hegigi used in this year's NACL, and this was also for summarization. Okay, so here's this graphical model representation that I showed earlier from the Barsley and Lee paper. And basically what we're proposing to add to this is the following. So we've added a hidden state here for each word, which determines which source it was drawn from. So it could either come from the dialogue act, it could come from the topic of the conversation, or it could just come from general English. And so in order to do inference in this model, we used collapsed Gibbs sampling, which is just a standard technique for this kind of thing, where we sample each variable in turn, conditioned on the assignment to all the other variables, integrating out the parameters. But we found that there's a lot of different hyperparameters that we have to set. And these things actually really affect the results of the output. So to solve this problem, we tried doing a giant grid search at first, but this was just kind of infeasible. So we used this idea of sampling the hyperparameters, where we just treat them like other random variables and just sample them in the Gibbs sampling procedure. And we used this slice sampling approach, which we found to work pretty well. So another big problem is probability estimation. And so this is basically the problem of estimating the partition function, which is intractable in these kinds of models in general. So we need to use some kind of approximation. And I'm not going to go into a lot of detail on this, but we just use this CHIB-style estimator, which has been proposed recently in the literature for this kind of thing, and we found that it worked pretty well. Okay, so we did a qualitative evaluation. We trained our model on 10,000 Twitter conversations, and then sort of looked at the dialogue acts it generated to try and see if they make sense. And so what I've shown here is a visualization of the transition matrix between dialogue acts. So each numbered box represents a dialogue act, and an arrow is drawn between 2 acts if the probability of that transition is higher than some threshold. And I believe I set it to like 0.15 here, and there's about 10 acts, so it's sort of like higher than random chance. Okay, and so now in order to visualize each of the acts, I've shown a word cloud where the size of the word is proportional to its probability of being generated by that act. And so you can see that this act in particular is sort of a starting state. It sort of starts a conversation, so it's transitioned to from the start state. And it has the word I with very high probability. And then you'll also notice that it has a lot of words like today, going, getting, these kinds of verbs that describe what someone's doing. And you'll see a lot of words like tonight, morning, night, today, tomorrow, a lot of sort of time words. So this is just sort of like this typical kind of post on Twitter where someone's just describing what they're currently doing. And this sort of, I think, makes a lot of sense. So this one can be transitioned to from any of the initial starting posts. And it's pretty clearly a question. The question mark has super high probability. And then you also see that you has very high probability here, whereas in the previous one, I had high probability, but you don't see you. And then you see things like what are your, etc. And then this act is also a question, but this is sort of an initial question that's starting a conversation. And so this one, you'll see a lot of the same things as the last question state, but there's also some words that we didn't see. So you'll see things like no, anyone, why, who. And from looking at some of the examples, it seems like this is really someone just asking a question to their followers, and it's typically sort of asking for an opinion about something. And then this one's a little bit different. So in just the pre-processing of the corpus, I replaced all the usernames with this user tag and all the URLs with the URL tag. So this one contains a lot of usernames and URLs. And it also has this word RT, which has sort of special significance in Twitter. It stands for retweet, which is like reposting someone else's post that you found interesting. So this is sort of like broadcasting some interesting information you found, And sort of in response to this, we see this sort of reaction state where the exclamation point has super high probability. And you see things like haha, LOL, thanks. You can just imagine sort of like reacting to some funny link someone sent you. Okay, so we also did a quantitative evaluation where we try and measure how well our model can predict the order of the sentences in a conversation. And so in order to do this, we had a test set of 1,000 conversations. And for each one of those, we generated all possible permutations, all sort of n factorial permutations of that conversation, and evaluated its probability under our model. And then we picked the one with highest probability and compared that ordering to the original sentence order. And so in order to compare orderings, we used this Kendall-Tau metric, which is basically a correlation between rankings. So if the two rankings are exactly the same, the value will be 1. If they're exactly opposite, the value will be -1. And anything greater than 0 is like a positive correlation. Okay, and so here I'm just showing some experimental results. So this is from the content modeling approach from Barzilay and Lee. And these are all trained using EM, and we're using various levels of abstraction. So we tried using part-of-speech tags and then word clusters, but it turned out that just using the raw word unigrams worked best in terms of recovering sentence order. And then our content model, our conversation model with the topics included does a little bit better. It gives sort of a nice boost. However, we found that when we just leave the topics out and just use the fully Bayesian version of the content model, it tends to do a little bit better. And I tried running sort of a whole lot of experiments to try and sort of get the topics working. And I mean, they beat the EM version, but we weren't able to get them to beat the just fully Bayesian content model. And so why is it that the fully Bayesian content model is winning? So it could be outperforming the version with the topics for a couple of different reasons. So for one thing, it has fewer parameters and hidden variables to set. So this could just be a problem with getting stuck in a local maximum. In addition, it could be that modeling the topic transitions is actually important in predicting sentence order. So even though it doesn't give us really nice-looking dialogue acts, it could be just important for that task. And so in terms of why it's outperforming EM, I don't think this is super controversial. There's been a couple other papers that show that this full Bayesian inference is better. And there's a couple possible explanations for that. So we're integrating out the parameters. We're not just using a maximum likelihood estimate. And we're also estimating the hyperparameters from data. And this gave us a little boost, but I don't think it's sort of explaining all of the difference. But I think it's probably most of it is due to the sparse prior. So in EM, or in the standard EM, you can't sort of use the sparse prior, whereas with the Gibbs sampling, you can. And actually, the hyperparameters that we found were sparse, so it was actually using it. Okay, so in conclusion, we presented a corpus of Twitter conversations, which we're actually planning, I believe, to make publicly available now. And we showed that they have some sort of common structure, which looks like it would be sort of interesting to exploit for applications. And we showed that the Gibbs sampling and full Bayesian inference seems to outperform EM. Thanks. Yeah.
I don't tweet much. Can you tell us again how you identify what constitutes a conversation? Are you bound to that?
Right. So basically, when you hit the reply button, it sort of stores that information. So just in the API, it has sort of like if the tweet's in reply to something, it'll have the ID of the post that it's in reply to, and then you can just query for that, and then from that one, if it's in reply, query. So it's just sort of chain it back, Does this make sense? Or?
It does, but I think you may have you may identify things as conversations that really aren't.
So like how so? What do you mean?
Tonight I say, hey, you want to get dinner, and you tweet back tomorrow. Sorry, missed your message. Those are related. That's kind of conversation, even though it spans a day.
Right.
The following day, I text you back.
Yes.
Something totally unrelated.
Yeah, you're probably right. That probably does happen in our data set. I think most of them are actually real conversations. There are a lot of cases where we sort of miss part of the conversation, like they forget to hit the reply button or something, and we get these sort of two parts of it that are separate. So there's issues like that with the data, definitely. But for the most part, I think it looks pretty good. Yeah.
Again, I don't tweet, I don't follow Twitter, but it seems to me you have one person posting something and then several different people replying, so that's not one coherent conversation.
Right. So when it's sort of a conversation tree, yeah. So we tried to like we tried to explicitly filter out the multi-party conversations just to try and keep the data clean. But yeah, you could have sort of multiple conversations that began with the same tweet. And yeah, that is kind of, I don't know, I'm not sure the best way to handle that. But yeah, that's a good point. Yeah. Uh-huh.
So you had ways to go up the conversation. Is there any way to go down the conversation?
No, not that I could figure out at least. So that is kind of a problem. So we might not see the very end, you know. So, or I mean, even if you think about it, just going in time, if we pick something that happened right now, we don't know that the person isn't going to reply. So I think that's always just going to be a problem. Yeah.
You mentioned that you were looking for trying to pull out things like status and comment, thanks, questions, stuff like that as the categories. Did you come up with those ideas a priori, or were those based on examining what the model found?
Yeah, so those are just sort of my interpretations of what, you know, the clusters look like, basically. You know what I mean? So there was no labeled data. This is all totally unsupervised, and it just sort of found those clusters just by itself, you know. Yeah. Sure. I think you were first.
So I'm wondering here, you're doing what? I guess two questions. So tweets and Twitter seems like a very small domain, actually, and this particular problem you're looking at is very similar to like email threads or like Facebook conversations, and there's a whole genre there.
Right.
Have you thought about extending it or expanding it or trying to relate it some kind of way to other similar kinds of electronic communication? I don't even know what to call it. Genres is a good word.
Yeah. So there's a lot of things like IRC chat and Facebook and so on. I think Twitter is good for this because it's the default setting on people's accounts is open, totally public, so you can go crawl it. Like Facebook, the default is private.
Okay.
So it's sort of harder. And I think people have looked at email and stuff too. Yeah. But was there a question? Yeah.
Well, you kind of answered. It was leading up to my question. He kind of went into it, and you half answered it. I was going to ask why you chose Facebook, why you chose Twitter instead of Facebook. Was it because of, and I'm also thinking because Facebook would have images and video and
yeah, but Twitter actually.
Twitter's all text.
Twitter actually does have images too. There's like this tweet pic or something like that. People will put links to pictures, you know, and be like, haha, look at this, you know, and it's, I mean, that you need some vision algorithms or something to handle that. I don't know. But yeah, Peter.
So you had about 10 nodes in your transition graph there.
Yeah.
So did you have to choose a threshold for your clustering? How did you choose that? So.
You mean picking the number of clusters? Is this your question? Yeah, so yeah, we picked 10 for that, mostly just because it's easy to visualize, you know what I mean? So I think the best performing ones, I think were about 20 clusters, if I recall. So we did vary the number of clusters and look at that. Yeah.
So when you parsed, it was all strictly straight off of like the original, like the @ and then the username, or did you, or if the user put in like directed at someone, while in the middle of the message, did you catch that too, or?
So I think your question's about usernames. I'm not sure I quite got it.
Well, like sometimes when you caught when it started a conversation, was it simply because through the start you catch the username at the beginning, or was it through like, or what determined?
Right, I think I see what you're saying. So so there's a convention that if you put the username at the beginning of your post, you're directing that at that person. And so that wasn't actually, we didn't use that to get this data. So what we did is if you hit the reply button, then Twitter actually records that as like this post was in reply to this other post, you know what I mean? So trying to recover the conversations just using the username I think might be a bit difficult. I don't think it would be as, because you don't know sort of like you don't know really which post it was in response to, you know what I mean? Yeah.
Well, I was just thinking that with the usernames, if I remember correctly, Twitter, if you look at somebody's profile, you can see all the people that follow them.
Right.
So it seems that if you're looking at words that happen in a particular post and grouping them by that, you might be able to look at a particular user and their followers and recreate reconnect conversations that weren't using the reply.
Right, yeah, so I think it's a little bit more, because you're never going to know exactly which post it was in reply to. So, I mean, one user could say a bunch of things, and then another user could say a bunch, you know, and sort of, I mean, I think it would be sort of an interesting problem to try and do that. I think you'd need some sort of, like, non-deterministic thing to figure it out, you know?
Yeah, I'm just thinking that, yes, one user might say a whole bunch of things which a different user responds only one thing, but that's how conversations tend to go. One person is going on and on and on, especially given the artificial length limit on Twitter. So.
Right. That's a good point. Yeah. And yeah, I mean, there's work people have done on IRC chat logs on trying to disentangle conversations, you know, like there's multiple threads going on at the same time. And yeah, no, I think that's would be interesting to address. Yeah?
So part of your presentation was an example of styles of conversations. Kind of following what you just been on, is there a way to take a part of conversation which you may have built from followers and find out if it's a particular stage in a set of conversations?
Yeah, that's a good question. Yeah, we didn't look at that at all, but yeah, I think sort of, yeah, I mean, you could take sort of fragments of conversations from different users and sort of like try and see, you know, are they connected in any way? We haven't looked at that, but I think that would be an interesting thing to do. Yeah.
Perhaps you could address this in your presentation, and if you have, forgive me for asking the question, but in terms of the structures and conversations in Twitter, what would you be able to do? How could that help? Let me ask you, in terms of technologies and stuff and the structures and stuff, what will that be able to do for, I guess, future technologies? I mean,
so you're just asking about like applications?
Yeah, applications.
Yeah, right. So yeah, I gave sort of like a brief sort of motivation for this at the beginning. I mean, I think sort of like I kind of mentioned the idea of sort of like building a conversational agent, you know, I think is sort of like a big, was sort of the driving thing for us at the beginning of this project. Yeah.
What about search? I mean, do you think that could play a role in search and stuff? To build better search technologies?
Right. So I think if you're trying to like search facts or like message boards or something like that, I think something like this might be helpful. Like if you're looking for things that are an answer to a question. I don't know. I mean, honestly, I haven't spent sort of a whole lot of time thinking about this. But I think, I mean, it seems like you should be able to help with this kind of information somehow, like how people are searching conversational text, you know. Yeah.
Do you think there's added value from considering the timestamps on the tweets? Like certain types of conversations might be faster or slower?
Right. Yeah, so I think I noticed most of them seem to take place within a time span of like 20 minutes or something like that. And yeah, I think that's a great thing to look at. It could somehow indicate some important information. I can't think of off the top of my head what, but yeah, I mean, another thing too, a lot of these things are sort of like happening on mobile devices, so maybe the really quick conversations are more likely to be on mobile than on the web interface or something like that, but yeah.
Going to the time, did you notice say there's a type of conversation, say at 2 a.m. versus 2 p.m.? Was there experience?
Right, yeah. I mean, there's definitely the frequency of tweets definitely varies a lot by time. So like at night, there's I think there's fewer than during the normal hours in North America or something like that. But yeah, I don't know about the types of conversations. I didn't look at that. That would be an interesting thing to look at. Yeah, I don't know. It's a good idea.
This is off topic, Alan, but what did you use to make the tag clouds? Did you do it by hand?
No. There was just some like sort of web interface with a Java applet called Wordle, I think it was called. Yeah.
Thanks.
Yeah. Okay. Cool. Thanks.
Okay, so now we're going to go from the short tweets to the long protein names and long concepts in biomedical. So this is Hoifang Poon, and he's done some work with Lucy van der Wende on joint inference for knowledge extraction from biomedical literature.
Okay, thanks, Michael, for the introduction. So this summer, I have the great pleasure working with Lucy on this exciting project of joint inference for event extraction. For those who have been to my intern exit talk, it's pretty much the same talk with a compression ratio of 3. I will start with some motivation, and then I will talk about the task of bio-event extraction, and finally I will present our system and some preliminary results. So before we dive into this bio-event extraction, let's step back and take a look at the bigger picture. So in the past decade or so, with the advent of the World Wide Web, there emerged a great vision of knowledge extraction from the web. And the idea is that to go from the unstructured or semi-structured text available from the online and turn them, extract structured knowledge from them. Such a great vision doesn't really need much advertisement beyond itself. Apparently, if we can extract knowledge automatically and reliably, even within a limited extent, we will construct a gigantic knowledge base, probably the largest in the world. And then this can facilitate all kinds of great applications like semantic search, question answering, and so forth. And finally, by breaching the knowledge acquisition bottleneck, the days towards solving AI could be numbered. So in the past decade or so, this is a great vision, and there has been some very great efforts spent, including some local system like very notable system like TextRunner and MyNet. However, the problem still remains largely unsolved. And the natural question to ask is, should we start looking at tackling the whole web as a whole from day one, or is there a domain that we should set priority on? Presumably, such a domain either would be more urgent to tackle, or maybe it's easier to make progress on. And also, the lessons learned and also the infrastructure we build for this domain should be general so that we can use it for a starting point to tackling the rest of the web. So I will argue that the biomedical literature is such a great starting point for knowledge extraction from the web. So online from PubMed, there are about 18 million abstracts right now. And this is and then the growth is exponential. A few years back, the reported number I saw is about 14 million. So you can do the math. And the success, if we can have some success here, that will have a huge impact on biomedical research. So when you do biomedical research, you have to have access to a broad spectrum of information. Like if you're investigating a disease of diabetes or AIDS, the relevant gene, the number of relevant genes might be in hundreds or even thousands. So you really want to know all those relevant information. And on the other side, each gene under the sun might have already been investigated by some lab somewhere, sometime. However, those information is captured, maybe written out in a nice paper, but it's buried under this millions of articles, and it's very difficult to find them out for researchers. So one biomedical research student at UW actually told me that they couldn't really keep up with all the literature in their own subfield, and what they do is they really just follow a few top labs and just pay attention to what they do. So you can imagine how much research effort has been wasted because of this, and also how many discovery opportunity has been missed as a result. And also, needless to say, if we can make progress in this direction, there is also a flip side on the commercial world that this will bring a huge impact to the drug design, and also the big pharmaceutical company will really love it. And finally, this domain is attractive for this, especially for this audience, because they're all written in grammatical English. So from a particular previous talk, you have already seen some of the English may not be, some of the language there may not be so amenable to processing. However, in this domain, you're supposed to write in grammatical English, and so you can, mostly in English, and often in English, and you can apply any of the advanced linguistic theory or NLP2 to this domain. So hopefully I have convinced you that this is a worthy endeavor. However, another natural question to ask then is why is this problem hard? So here, to get a feeling about the domain, here's a typical snippet from one of the sentences in one abstract. So this is not even a full sentence. So you can see this few number of characters actually encode a great number of knowledge there. So it actually describes a bunch of events marked in red here, and also describe a bunch of protein and genes marked in green here, and also some of the localization site marked in the blue. And supposedly, this actually conveys a complex nested structure. So you have an up-regulation event, you have another regulation event signified by the involvement, and yet another one by activation, and then they also have the event argument structure, like the IL-10 is the theme of the up-regulation event, and also the psi and the cause and so forth. So you can imagine using shallow techniques like keyword search or pattern match is really couldn't really scratch even the surface. So this is the first major reason why the information is so hard to get. Another major reason, which is sort of really common to NLP, is that you can say the same thing but in many, many different ways. So here is what's called a trigger word that sort of signifies the event for negative regulation, and just within 1,000 documents, 1,000 abstracts from the PubMed. So you can see the numbers are basically the number of times that following word are used to signify the event, and this is, you can see this is clearly a long tail. On the flip side of this, the same word can also mean very different events. So for example, in this corpus of 1,000 abstracts, the word appearance is actually used to signify 5 different event types, so including some of the examples here. And also, there are some very subtle denotation. Like for example, in this sentence, you can see the first line, these cells are deficient in some expression, although their productions is normal. So normal here actually signify regulation event, but if you just look at the second part of the clause, just look at this subclause, some production is normal, you rarely get a clue of that of an event. Only when you consider that in terms of the context that there is a parallel event that's described earlier, then this is actually referring to the same event, but talking about that this event doesn't happen in this context. So by now you have seen that why this problem is hard, and in fact this is actually a great opportunity for common linguists and NLP researchers, and exactly because of all this complication involved in the human languages. So bio-NLP is actually an emerging field. It has right now it is a regular workshop in NACO or ACL, and I won't be surprised if it will become a full-blown conference very soon. So initially, the community started on tackling just trying to recognize a protein name, and this problem is largely solved. We can get to high 80s. And then they venture into trying to detect whether two proteins interact with each other. So this has been going on for a decade or so, but still the top F1 is around 60. It's largely unsolved. And it's actually mostly because when people work on this problem, they recognize that, in fact, instead of working on just treating it as a binary classification using shallow method, it's actually necessary to go deeper into the language structure and actually tackling, extracting the detailed bio event. And this is so this is the shared task of this year. And obviously, the story doesn't end here. There has been already effort going on to construct a pathway corpus, and then eventually you want to build entire gene network and understand how they interact and so forth. So in this talk, we'll focus on this bio event extraction. And so by definition, a bio event refers to state change of biomolecules. And so in this shared task, they focus on these 9 event types. So the first 5 event types are relatively simple because they can only take one theme. The binding is a lot more complicated. It can take up to 5 themes, so you can have A binds to B and C and D, so forth. And then the regulation, and they distinguish regulation into positive, negative, and also ambiguous, which you don't know which way to go. And this is the most complex, as we'll see in an example. So the data given to the shared task is that you are given the text, obviously, and then you are also, because protein recognition is a problem that is largely solved, we want to factor it out from the task. So they also give you where are the proteins. And then your system is supposed to predict this block of information. So each line either refer to sort of an event type declaration or an actual theme or cause. So the first two lines talk about that there is a regulation event signified by the involvement, there is a positive regulation signified by activation, and then the last two lines actually talk about, so E1 is an event, and it takes the theme of E2 and cause by T3. So here you can see that a regulation event can take another event as an argument. So you don't have to look into the number. The whole point for this slide is that this shared task has attracted a great number of participants, and as a result, the performance are pretty representative of the current state of the art. And so the top system is by a group from University of Turku from Finland. So on the simple event, the first 5 events, they get an F1 of about 70, which is pretty decent. However, on the binding and on the regulation event, those are the really difficult ones. And overall, the F1 is about 52 and the precision is about 58. So both are not, still not very satisfying. And then the top system also have another problem at the high level, is that they adopt a pipeline architecture. Actually, the top 3 systems all adopt a pipeline architecture. So they typically first determine a number of candidate events and types. And then starting with this list of candidates, they then classify for each pair of this candidate and a protein, or between the 2 candidates, whether the latter is a theme or cause of the former one. So, and then this Turku system uses SVM for classification. So a major drawback for this approach is that there is no way to feedback information once you have committed to the list of candidates. And the Turku system actually has to do some very ad hoc engineering to facilitate the second stage learning. And also, another major drawback is that the prediction of each theme or cause, or also each event and their types, is made totally independent of each other. So you actually lost a lot of opportunity to inform the decision. As another interesting data point is the Tokyo team, they use the conditional random field, and they are actually from the organizer, and they get an F1 of 37. So the bottom line is this task is very challenging, indeed reflecting how complicated is human language. So when we come to decide our system, our first decision made is that even though the top system all use the pipeline architecture, we think that that's not satisfying and that's not good for pushing the performance towards the next level. So we think the first criteria is to jointly predict events and arguments. And also there are certain prior knowledge that we know and we want to incorporate straightforwardly. And moreover, when we saw that the conditional random field doesn't cut it, because from the inside it's really obvious, because the label doesn't really correlate in terms of linear context. But they are probably likely so in syntactic context. So for example, if you know that B is the theme of A, and then C is in conjunction of B, like B and A, like regulate B and A, then you will conclude that maybe C is also a theme of A. So because of this, we pick our framework. We pick Markov logic as a framework. Markov logic is a framework developed by Matt Richardson and Pedro Domingo. and it can compactly represent very complex relations and also handle the uncertainty. So the bottom line is that you have, basically each Markov logic network consists of a pair of first-order logic formulas together with a weight. And this defines a joint probability distribution using a log linear model. And the Ni here is the number of true grounding. So you don't really need to pay too much attention to the technical detail. So in the interest of time, I skip the examples. So Markov logic is a natural framework to conduct joint inference. And moreover, there has been already a lot of efficient algorithm available and in an open source implementation. So our Markov logic network for the bio-event extraction consists of a few formulas. So the first group of formula basically, so another advantage of Markov logic is that you can express this into intuitive regularity very compactly and straightforwardly. So for example, we have the prior knowledge like event must have a theme, and regulation event only can have a course and so forth. So we incorporate those as hard constraints. And then there are those soft evidence, like for example, activation. The word activation probably refer to a positive regulation event. This doesn't hold all the time, but it holds statistically for quite a number of cases. And then there is this syntactic evidence, which we already mentioned, like for example, conjunct of a theme is likely a theme as well. And finally, there is this lexical, combining lexical and syntactic. So for example, the subject of the word regulate is probably signifying, actually this should be a cause, sorry. These last three groups, basically the alchemy can learn way for each specific constant. So you can specify very compactly with a few rules, but then it will learn, oops, sorry about that. So our base MLN basically consists of the first two, the first three rules, you can consider them as a joint inference rule because they basically can make decision for between events and themes and also different themes and events together. And then the base system consists of the first two rules and then the lexical evidence and the syntactic evidence. So here are the preliminary results on the development set, and it's evaluated on the ground atom, so not entirely the same as the evaluating on the events, but this give us an idea. So we get a F1 of 64, and more importantly, we get a pretty high precision of 74. And let's take a look at the effect of the features. So if we start with just the base MLN, it get the F1 of 34. But as long as we add the first joint inference rule, we get a huge improvement. And then if we add some lexical evidence and also some preprocessing, we get to 64. And also, we see that the training, so here the training size is represented by the number of abstracts. So we can see that going from 50 to 100, we get a huge improvement, and then it starts to level off. So here are the number for just on the event types, like whether our system can predict the event type correctly. So for those who have seen my last talk, this number is slightly better because I have some new results. So what you can see is that the first few type of events, the F1 is already pretty high. So one idea would be to actually start using this extraction. Maybe we cannot use this for all the events, but we can start using this most accurate one to start building a community or attracting initial consumers and etc. And also another take-home message from here is that in general our precision are pretty high compared to the participating systems, and this is arguably good for this domain because whatever you propose better to be correct. It's okay to miss some, but what you propose better not to be a whole lot of noise. So in future work, we want to incorporate more joint inference opportunity. You have already seen some candidate in earlier slide, which we haven't been able to incorporate in this MLN yet. We definitely want to incorporate discourse, like co-reference, like whether intro sentential discourse, co-reference or intro intersentential ones. And those is another special kind of joint inference. And then finally, we may start looking into some application to some product, commercial product. So in conclusion, I have presented a system for joint inference for bio-event extractions. It's based on Markov logic. The preliminary results is pretty promising, and also our system, because of the benefiting from the joint inference, it tend to attain higher precision. And finally, maybe we can start thinking about some commercial application, focusing on the most accurate ones. Thank you, and I would like to take questions.
So, yes. So do you assume that the theme and cause, they occur in the same sentence as the event? Or are you assuming that the theme and the cause of an event will occur in the same sentence?
That's an excellent question. So, actually, no. The shared task and notation, there were a number of cases where the theme are actually stated in the previous sentence, and then later on they are referenced by co-reference. There were like about 5% of them, and currently our system didn't address that. I think none of the existing system addressed that, but that's definitely an opportunity. You can see something like they mention a bunch of genes, and then you have sentence like these genes are found to blah blah blah, and so forth. Yeah. Yes.
I'm wondering if the Markov logic approach would allow you to incorporate information from the big ontologies they have in this domain, so you could get more out of small training data.
Yeah, that's another great point. And in fact, we have considered actually something along the same line, but it's sort of more like using some unsupervised approach to sort of construct some like clusters, and then to sort of multiply the training data. So I haven't quite thought about using the Agenia ontology. The ontology per se might yield some information, but also there is a question like because none of those textual expressions are marked with those are directly related to the ontology. So you have ontology available, but then you also have text, and then there is a mapping between text and ontology. So that's always a problem for formal ontology. I think if we can somehow construct sort of like a text-based ontology, maybe unsupervised from the text, then it's much easier to relate them, and then we can start multiplying training example that way. So that's an excellent point.
So do you actually need to specify all those features before you do the training? I mean, all those
yeah. So this is totally supervised learning, and we don't do any structured learning. But so you do need to specify the feature first.
So how many features are there? Roughly
So there are roughly about I would say between 10 to 15 rules. So Markov logic, one advantage is that there is some syntactic shortcut that allow you to specify in one rule, and then the system will learn way for each combination of constants. So for example, you can specify a rule saying, I try to learn way for each individual word, whether what event type is signifying, and then it will try to learn way for activation, regulate, and so forth.
So you have the hard constraints that each event must have at least one theme. Mm-hmm. Did you find cases where the theme just wasn't mentioned in the text?
That's a great question. So this is more like artificial effect of how they annotate this shared task. So when they share annotate, so there is another issue that I didn't get into in the slide, is that how they annotate the shared task data actually also play in some difficulty for the learning and training. So in particular, they have to they will only annotate event if it has one theme, that can trace down to a protein, and it is explicitly stated. So if you have, like say, you could have a sentence saying IL-2 regulates something, but if that something is not protein, this whole thing is not annotated. So that actually makes the training a lot trickier from the inside. Okay, thank you.